Welcome to Crack It. Today we are going to discuss about what is race condition in Java along with the example. This has become a popular multi-threading interview question in the recent days. Before we know what race condition is, we need to first understand what is critical section. So a critical section is nothing but a block of code which is accessing a shared resource and that can be executed by only one thread at a given point of time. I've taken this example from my previous video, which is singleton design pattern. I'll pin its link in the comment section. You can use that if you want to know more about it. If we look into this piece of code, we can see that we are creating a new instance in the synchronized block. So this creation of new instance is critical section for our singleton class. Why? Because the purpose of singleton is to create only one object and need to return that single object all the time. And if multiple threads access this line of code in a given time, there is a chance that multiple objects will be created for this class, which is the contradiction for its principle. As we are now clear about what critical section is, let's move on to race condition. What is a race condition? The race condition is a concurrency issue that will occur due to the concurrent execution of the critical section by multiple threads without proper synchronization. That is, the threads have access to this shared data and they try to change it at the same time. In such scenario, threads are racing each other to access this data, and this condition is called race condition. So, what are the types of the race condition? We have two types in the race condition: read, modify, write, and check, then act. We will see both of these with example. Let's now understand what read, modify, write race condition is. This is a type of a race condition which will occur when there is an improper synchronization of non-atomic operations or a combination of two or more individual atomic operations which together are not atomic. So let's try to understand this with an example for the better understanding. So I have a class here wherein I have a counter variable and I am incrementing this variable inside my increment counter method. Suppose let's consider two threads T1 and T2 that are executing this increment counter method. We won't know when the OS switches between the two threads T1 and T2. This single line of code on the increment counter method will not be executed as a single atomic operation by the Java virtual machine. It will be splitted into smaller instructions. For now, let's consider the OS has executing this as three smaller operations. First being read the value of the counter from the memory, second being incrementing this value, and third being writing this value to the counter variable again. So let's now see what will happen to the value of the counter if the execution happens in the combination. So T1 will read the value of the counter, which will be 0. T2 will be reading the value of the counter, which will be 0. So T2 got the chance to execute and T1 will go to the sleep mode. So T2 will increment the counter by 1 and the counter value and write its value to the counter, which is 1 now. So counter value will be 1. Now T2 is going to the sleep mode. T1 comes to the execution, but T1 already read the value of the counter and it has 0 in its cache memory. So it will increment the counter. 0 plus 1 is 1 and the T2 will write this value of 1 to the counter. So the two threads want to increment the counter during the execution and the expected counter value is 2. Why? T1 is incrementing the counter value by 1, T2 is incrementing the counter value by 1, so the expected value is 2. But however, since the execution of this threads is mixed, the result is not as we expected. So to fix this race condition in Java, we need to wrap the code inside the synchronized block, which will make them atomic together, because no thread can go inside the synchronized block if one thread is already there. Let's now understand what is check then act race condition. In this type of race condition, two or more threads check the same condition and then act based on the result of the condition, which may also lead a program to a data inconsistency problem. Let's understand this through an example. We have a method wherein we are accepting x and y as the input parameters, and if the value of the x is 6, we are multiplying the value of x by 2 and assigning it back to y. So what is the problem here? Consider we have two threads T1 and T2, both reads the value of the x. T1 continues its execution, but T2 went to sleep for some reason. But the value of the x is changed to some other value, say 5, in the meantime, but that is not reflected in the T1. When T1 got its chance, ideally it should not execute this if block since the value of x got changed, but T1 is not aware of that change. It will come inside the if block and execute this block, which is the data inconsistency problem. And this condition is called as check then act race condition. To prevent this type of race conditions from occurring, we need to put a lock around this shared data to ensure only one thread can access this data at a given time. So in our example, we have added a synchronized block for this if condition, which will avoid this inconsistency issues. So how can we prevent race condition now? This race condition can be prevented if the critical section is treated as an atomic instruction. That is nothing but a proper synchronization. What is proper synchronization? When a thread starts its execution in the critical section, then no other threads are allowed to enter it until the thread leaves this critical section. The proper synchronization can be established using the synchronized blocks or the synchronized constructs like locks or the atomic variables like the atomic integers. The examples that we mentioned are really simple in daily coding. This may be even more complicated. Thanks for watching Crack It. Please do like, share and subscribe.